say good afternoon to you. I'm Alan Pitts, W1AGP, the Media and Public Relations Manager for ARRL. And this is the next one of a whole series of do-it-yourself projects. I am very pleased and happy to welcome John Best to the ARRL Expo. And he'll be talking about microcontrollers. If you're interested in these, and I hope John will get you interested, over that away, by the way, ARRL has a place set up where people are making and programming and working and creating these things. I know if you're like me, you've probably got a pile of stuff in your shack that was made by MFJ. They make nice stuff, but at the same time, isn't it a whole lot more fun when you make it yourself? Even if it blows up, it's kind of interesting and fun to do, and that's why we're hams. So this is called Do It Yourself. So, John?
Thank you very much. I think I'll move this enough so you guys can see without having the whole thing. Is that good enough? Great. So let's see if this works. We'll just flip the second slide. So there are a number of tutorials that are related to this one that are going on yesterday, today, and tomorrow. And this is the set of ones that are being done by the group of guys that I'm working with. And we have a booth right in the back of this hall for the HamStack Sierra Radio Systems group, and you kind of see all the stuff that I'm going to talk about there, and get started yourself with that. But one question is, did any of you see George Zafiropoulos' talk yesterday? Okay, at least a few. And he has a good introduction to the whole thing, and he's going to repeat it again tomorrow morning. So that might make sense for you to see that if you didn't see that yesterday. So the Sierra Radio Systems that I'm with, we got our start making repeater controllers for big link systems. So it's up to 8 ports where you have multiple links pointing in different directions, maybe several, a 440, 900, 2-meter repeater on the same thing that needs a lot of control. And that's an example of what we built. We did a lot of microcode to do that, and it was all built on the microchip PIC processors. And we started thinking, we learned a lot from how to do that, how to do real-time systems, doing interesting things. The code was fairly complicated. And then we wanted to do little projects, and I'll show you about one of the ones that I wanted to do. And it was virtually impossible to pull apart the code from this and do a little project. So that got us motivated to make something that was much easier to get started, do little projects, and then we thought maybe that would be useful for other people to do their own little projects. And so out of that grew something we call HamStack. That's a small little microcomputer that you can plug I/O boards on top of, or plug it into substantial I/O boards, and we'll talk about some of those and how to program those as we go along. So the first thing is a brief introduction to microprocessors. Most of you guys probably know this, so I'll go fairly quickly, but if you don't hesitate to ask questions. The basic microprocessor system on a chip, they sometimes call them today, will have in one chip not just the computer itself, but all the memory to operate and a bunch of I/O peripherals. Include various random digital output to set pins, can read things in. It'll have a serial port controller, complete UART. May have pulse width modulators to do analog output, A to D converters, timers, all kinds of things built into one chip. A bunch of different companies make those today. Atmel makes them. Those are the ones that are used on the popular Arduino boards that are kind of similar to what we're doing here. Microchip makes them. I'm going to be talking about the microchip part. There are many other boards that are built on top of those. Again, the Arduino, Basic Stamp, the HamStack. That's our board, and so our talk will focus on how to program this combination, but a lot of the basic concepts apply to any of these. So inside one of these PIC microprocessor chips, is they'll run up to a 64 megahertz clock rate. They do 4 clocks for 1 instruction. So basically 1 instruction 16 million times a second. So you can get a lot done in that. Can't do big fancy GUIs like on your PC, but you can do a lot of control kinds of things. They include, again, all the memory, and then they have a bunch of IOs on them, timers, A to D converters, UARTs for serial, hardware support for various serial interfaces to connect to other chips. I2C is one that we use a lot. Some of them even have Ethernet MAX built into them that you can just plug into that. So a lot of I/O all built onto these single chips. The particular one we're using, and we've included on this board, is a microchip 18F4620, and there's a pin-compatible one that's a 46K22. K22 is their newer chip. It's a little faster and has some additional stuff in it, but other than that, it's the same. And you can see the basic specs there. Again, they can run 10 to 16 million instructions per second. Have a modest amount of memory. There's enough program flash to do some real program. The thing that usually constrains you is the amount of RAM for your data is pretty small. It's only a few kilobytes. There are lots of analog input and other various I/O ports. This is the board, the HamStack board that we built around that. You probably can't see anything on this schematic, but I'll point out a couple of the things on it. In the center is the processor itself. And basically all the processor pins are pulled out to the header pins on the board. Going back to that, so these header pins here, all the processor pins are basically brought out to those, so you can interface them to anything you want. In addition, there's one other chip on the board, which is an RS-232 level converter, so it's got standard serial port level there that you can just connect to. And then a small power regulator, so you can feed it with 12 volts and it'll run. This can't handle a lot of current, so if you've got a lot of I/O and other devices on it, then you need a little more power. But I've run LCD displays and even a GPS puck off this. It gets a little hot, but it works. So we'll start with the simplest program we can do, which is to blink an LED. And just so I get some background, how many of you have never programmed in C at all? So about half the audience. Okay. So here's the hardware we're going to use to do this. That is basically, it's just that HamStack board I just talked about. But the only thing that's really important for this is a crystal that drives the clock for the processor so that it's running, and an LED that's connected to one of the output pins. And in actual fact, I left off the resistor that's here to keep the current from being too high in the LED, but that's basically it. And on this board, it's that second LED. The first one's connected to power, and the second one is the one that we're going to blink. So any program to do things has a few simple pieces to it, and it's essentially you have some setup stuff to initialize the hardware. For example, in these microprocessors, you have to tell it that a particular pin is an output and not an input. So you got to go program to one of the registers that's mapped to a specific location in memory to tell it that's an output, and then basically in a normal program, you're going to read some inputs, make some decisions on it, write the outputs, and then you'll loop around and go and do that again. And you'll just keep doing that forever until you turn the thing off. In our case, if we're just going to blink an LED, all we're going to do is see whether the LED was on. If it's on, we're going to turn it off. If it's off, we're going to turn it on, and then we're going to wait half a second in between each one of those. So very, very simple program. And here's what the program looks like. And in C, this looks awfully complicated to do that. And let me go through briefly what that includes. First, these things up here called #include, that says take the files that are these file names and include them in, pull them in and compile them. And this first one is something that comes with the compiler for microchip, and it gives names and addresses to all the special register pins, so you can call them by name instead of having to know what the address is in your program. The second one enables some library functions that you'll see in a minute that use. So it basically tells the compiler about things that the library library has. And then these next ones you need to use to tell some certain hardware in the processor how to work, and it's specifically setting up the clock oscillator in the processor so that it takes that 16 megahertz crystal and it's using that on those 2 pins, and it's multiplying it by 4 to run the thing internally at 64 megahertz, and that's what this stuff does. And then we're defining a name for our status LED, and there's 2 bits associated with that. One is the direction that tells it whether that pin is an input or an output, and the other one is what bit in what memory location in the processor we use to turn it on or turn it off. And it's connected to pin C0 on the processor, and these are the names that Microchip gives to those bits on the thing. So then in the Microchip library, the delay functions that they include are just delay for a certain number of clock cycles. So basically, it'll sit there and spin in a little piece of code just running over and over again until you've gone that number of clock cycles, and then it'll go on to the next instruction. And they have 2 of them here that we use, one that delays for 10,000 cycles times the number of things we put in the argument there, and the other one's delay for 1,000 cycles. So at 16 million cycles per second that we've got, we want to delay 16,000 cycles per millisecond. So we've written a function that takes the number of milliseconds, and for each millisecond we're going to delay 1 times 10,000 and 6 times 1,000, or 16,000 cycles to get a millisecond. And then while MS minus minus in C means take that variable and decrease it by 1. So minus minus means just decrement it. And so as long as that is non-zero, it will do these 2 things, loop around again, and do these 2 things around. So if we put a 2 in here, see this is a 2, that's not 0. Then it'll decrement it to 1. It'll execute this, which will delay by 1 millisecond, and then it'll go back around again, see that it's 1, which means it's going to execute the stuff, decrement it to 0, execute this again, delays by 1 more millisecond. Next time around, it's 0, so it doesn't do this, and it exits the function. So then in C, your program always starts with something called main. And the first thing we do is we do the setup piece of the program. So that's this first piece up here, which is we define the output pin that the LED is connected to. We set it to 0, and that makes it an output. If you set it to 1, it's an input. That's just the way these processors work. And then we have an infinite loop, which is while 1. 1 in C is true, so that means while true, which means forever. We're going to do the things between this brace and this brace, and if our status LED out, so that's this little pin, is equal to 0, we make it 1. If it's equal to, and if it's not equal to 0, it means it's already 1, we're going to make it 0. So, and then we're going to do this for 500 milliseconds. So basically, we're going to, if the light's off, we're going to turn it on, we're going to wait for half a second. If the light's on, we're going to turn it off, and we're going to wait half a second, and then we'll just repeat. And so when you do that, you start, and you can see the light blinks. So that's all there is to it. That's your first program, and then everything else is simple after that to do interesting things. This shows we do the development on the tools that are free that Microchip has to do this software development. And it's called MP Lab, which is their integrated development environment, and C18 is their compiler that's used to turn C into the machine instructions. And the list of files that you're going to compile is over here, and your code is sitting in this window here, and it's probably a little hard to read, but it's exactly the code that we just showed 2 slides ago. And on the next, we'll see a PIC programmer that's a Microchip programmer connected up to the chip through the HamStack board. You can see the power LED is lit on, the other one's not lit yet. And here's the code that we had. And you see the cursor's up here, and it's first going to go and click that little icon, which is the one that says build the program, and then it's going to move over and click on the programmer one here and tell it to download it to the thing, and once it downloads it, you'll see the lights start blinking. So I'll start the video. You can see it goes and builds it, little screen comes up and it says that it's compiled it, and there were no little red things that said there's an error. If there's an error, it actually tells you where the error is. You can go right to it. And then it goes up to the programmer, programs it, and you can see the lights blinking. So that's the basic process for building your program. Now, that set of stuff you needed to do to set up the program was kind of complicated. You need to study the data sheet to figure out how to do that. So that's the thing, you want a library that somebody else has done that for you to make your program simple. So we built something we call the HamStack library for C that does all this stuff in yellow for you, and all you have to do is the stuff down here that generates the real core of the program. So that makes it a little bit easier to program. And so then in the end, the program that brings the LED looks like this. And what we actually did was we divided that main program into two pieces, an initialization piece and a piece that gets called over and over again that does the LED blinking. So this does exactly the same thing as that little bit more complicated program. And that's the basis for doing more complicated things, because we've got library functions that generate tones, generate CW, communicate with the serial port, and all of those are just going to be simple calls you do down here, and all the setup is handled by the library. So this is another way to write exactly the same thing. You don't have to use those symbolic names that we set up for this. You can use the normal register names out of the microchip data sheet if you want to do it and do the same thing. Wait long was another name for the same delay function. This is another version that I like that only people that love C will like. The little upward caret and equal says, take the exclusive OR of this with that, and an exclusive OR with one reverses the state, and then assign it back to the thing. So it's the same thing as if that else flipped the thing. So anyway, just C people like short little cryptic things that no one can understand that doesn't know C. But it makes the program shorter, so you'd have to type less. So to do more complex tasks, you need some sort of library that does more complicated things. So I got interested in this because I wanted to build a keyer, and it's kind of interesting. My keyer that I've been using for the last nearly 35 years was out of my favorite all-time issue of QST, which was the April 1968 issue. And the cover story had this schematic of this little keyer built with RTL logic with 3 integrated circuits. It was interesting. It was a graduate student project by a guy named Ron Stordahl, now AE5E. And the month after this, there was an advertisement in QST by a little company called DigiKey that sold this board. And later they stopped doing that because they were losing money on it, just like most of these vendors do. But later he went on and founded DigiKey, which is the large electronics distributor today. And that's why it's called DigiKey, because they started making this keyer. And that's my keyer that I built when I was in high school. The other cool thing in this particular QST was an April Fool's article, which I built and nearly destroyed my GX60 transmitter, but that's another story that was very educational. And that's why I love this QST, and I have like 3 copies of it that are in great shape. So anyway, when you want to do real applications that do things in real time, it gets kind of complicated, and on these little processors that can be hard to do. So why would you do it this way? And partly it is, when you have no operating system, you can actually understand everything. And there's no freeze, no hang-ups unless you make your own mistake, not somebody else's mistake. And this worked really well when we were doing that complicated repeater controller. It doesn't hang too often, as Mike back there, who has fielded several of them, has told me about the hangs that I did fix. And it's inexpensive, and it's a lot of fun to do. So to make it easier, our approach was to try and write libraries that make it easy to do the code, so you don't have to set up all the stuff yourself. And you use hardware interrupts, which we'll talk about in a minute, to do the more complicated things. So in the HamStack library today, we support a number of things. The ones that are not interrupt-driven, we'll talk about interrupts in a minute, are programming the EEPROM data memory that's on the chip, I2C interface, which is a little serial interface that a lot of chip vendors use to communicate with their magnetic compass sensors there, their temperature sensors, there are serial double EEPROM, lots of different things with that. We've played with a couple of these. One-wire interface, another serial interface. We've been doing a lot of digital temperature sensors with those. We've got an on-chip ADD converter support, PWM voltage output, I/O expansion, LCD display, so you can have a simple LCD display for your projects. Keeping track of time, calendar conversions, GPS position, time capture. We'll show some examples on these in a minute. Interrupt driven, so these are things that are going to happen in the background while your main program's running, and we've implemented a whole bunch of timers that will run at 1 millisecond intervals, so you can time things very precisely out to long periods of time. Generate tones, nice clean sine waves, not ugly square waves that sound bad. Generate CW automatically, so all you have to do is do CW send, and in parentheses the string you want to send, and then it just sends it while your program can go off doing something else. Generating DTMF strings, so again you just send it a string with the characters you want to send, and it just automatically sends it for you. Serial port transmit and received, shaft encoder, we'll show that in a moment. So again, the basic principle of all these is back to what we were showing before. You're going to initialize the program and hardware, you can read inputs, make decisions, write outputs, and then while you're doing this whole process, you're going to be calling subroutines that do a lot of the work, and it makes your program a little bit simpler. In a plain C program, there's a piece of initialization that the C compiler itself does. That's invisible to you. It kind of happens in the background. The C compiler does it. Then there's the piece where you initialize, like we had to set up which pin was the output pin for that blank. That's part of this main, that's the main program. And then you loop forever in the subroutine library. Some of those come with the C compiler, and some of them are ones that we've written in this HamStack library. In the HamStack library, you will write a function called userinit or user_once that does this initialization piece, and you'll write a piece of the user code that's down here, and there's another piece that runs in this loop that'll be background functions that the library is doing. So as long as your loop runs quickly, all the background functions will just happen without you worrying about them. And then the difficult thing is, if you want to do things really running in the background, multitasking, if you're going to put everything in this loop, you have to make sure everything happens really fast and doesn't have any long delays. So the way to do multitasking is use features in the processor where when an event happens in the hardware, it actually changes the program so it's executing code in a totally different location, does that. When it's done, it goes back to where you were. And that's called a hardware interrupt, and it saves sort of the state of where the processor is. It does whatever the hardware is, and then it restores a state. So in the processor, there are a bunch of little counters that are continuously counting with the clock. When one of those counters overflows and get to 0, it generates an interrupt. You can go over, then do something, and then it'll go back to your program. So using that, you can keep track of time. When a character comes in on the serial port, it generates an interrupt. So you can take the character out of the serial port registers and put it in a buffer or do some other processing on it. So these things can happen in the background while your program may be just waiting around in a loop doing nothing. And so in our library, we built a bunch of examples. Most of these examples are only 4 or 5 lines of code that then just incorporate the library functions to do them. Everything from just pushing a button or doing the blink thing we talked about to serial port input and output. There are 2 serial ports on the processor, so I've been connecting a GPS to one and my computer to the other, and this simple program will just let you communicate with the GPS without connecting it directly to the computer. Reading and writing an LCD character display, analog input, temperature, I mean, you can see all the things here. And then we've got some more complete projects, a CW IDer that every once in a while on time fires off an ID, a clock function that's set and synchronized to a GPS input, and the keyer, that's the keyer that I wanted to do based upon replacing that thing from the QST article. And so we'll just, we've written a manual that explains all this stuff, goes through the examples, and has reference for the library. And here's one very simple example, which is the serial I/O. And this one, if you can read this, it does serial gets, or serial readlin, which just, if you type something in, you hit carriage return, then this function will put all that stuff into the string S. variable, and it'll return true, and then it'll take the same thing and spew it back out the serial port. So if you're sitting there with a little dumb terminal program, you type something and you hit enter, you'll see it come back to you. So just an example of how to program that. This one is using an encoder. We've got the timers reading an optical shaft encoder, continuously keeping track of its position, and this will just, in a little loop, see what that count is and then output the current value to an LCD. And you can see that here. You can see the encoder twisting up here, and the count's going to read down here, and you'll see as you turn that, the count goes, and it's just that few lines of code to do that. So you can incorporate the same concepts into doing a more fancy user interface. So in our project examples, the first one is a CW keyer. It actually makes noise. It's impossible to hear in here because it's so loud, but if you want to see it later, so that was the first thing I did using this library. It has uses the shaft encoder and LCD display. It remembers its state it's in, so you can actually, let's go back before we do the details on that. It's built on top of the processors sitting on another board that we call the project board that has some analog filters for generating nice clean tones out of the pulse width modulation. It's got some relays on it that we're not using in the keyer. It's got an opto-isolated output that we can use the key to the transmit. It's got some digital inputs that you use to attach the key paddle. It's got a connection for a serial port. It's got a connection for the LCD. It's got a DTMF decoder on it. So a bunch of things so you can do interesting projects. This shows all the things that are on it in the schematic. I think I described basically what's there, so I won't go into more detail on that now. You have to hack it a little bit to do a keyer out of it in order to attach the this little encoder. These are only like $2. They're very nice, 16 counts per turn. And put it in a little box. And each time you push the button on the encoder, it switches modes from setting the speed to setting iambic mode A or B or whatever. Sets whether it's left-handed or right-handed, which was very important because I'm left-handed and can't key right-handed. You can set the weight, set the tone frequency. I forget what the last one is. Oh. If you attach it to a serial port, you can also send a long string of stuff with that. And this sets, if you set the speed to 5 words a minute, you can control what speed the characters are at. So you can have characters at 15 words a minute, even though it's widening out the spaces to send at 5, which I think is how the ARL code practice is set at slow speeds these days. And so there are lots of other things I'd like to do to this to make it fancier, but actually the clock function is already there now. But anyway, based upon the code's all there on our website, and if you want to play with this, you can enhance it yourself. Then the next thing we did was a clock, and so this was an idea of doing a clock that has built-in compensation for the error in the crystal, so it's frequency in the crystal, so it's really accurate, and it can be synced up to a GPS puck to set the clock. Another good example. We've got some battery backup stuff coming in, and we're working on new pieces on this. This shows the GPS puck that I like. Garmin sells these little GPS pucks for about $60, and they not only have the serial output of position and time, but they also have a yellow wire on it that produces 1 pulse per second, and the leading edge of that pulse is within 1 microsecond of UTC time. So if you want to do precise time things, you can do that with that, and we're using that. In this example, the output, the yellow output is from this, actually I don't remember which one's which. Anyway, the yellow, one of these is the output from the GPS puck, and the other one is an output generated internally in the hardware in our function in the HamStack library. So you can generate your own pulses that are at any time interval that are synchronized to GPS absolutely with this, and the library kind of includes the stuff to do that. And this shows just reading directly position and time, and now you know where my house is. And this shows the GPS clock synchronization, and this was kind of fun. When you turn the clock on, at first it comes up with sort of the default time, and if you wait around for 15 seconds, you'll see the GPS comes on, and I think that's when this gets to 15. It pops up and sets the time, and it's to within 1 millisecond. and I think I know how to get it to within 100 nanoseconds, but I haven't done that yet. So we were talking to some guys earlier today that wanted to do positioning triangular based upon time, and then the absolute time actually matters. So this was another, this shows how I was actually prototyping this thing. The final one sitting in the box here is we just have the CPU board sitting on this project board. I've got an extra lithium battery that goes into some pins that with a diode in it that's battery backup if you pull the plug here. Actually, this is the keyer with the GPS clock set. I had plugged in the GPS over here, and then it set the time, and so that was kind of fun because I like to have the time the UTC time next to my station. This shows a bunch of other things. We've been working on a magnetic compass sensor that some guys are putting up on their tower and their big antennas, and then radioing back the position with a 2.4 gigahertz link to measure the position. These little one-wire temperature sensors, you can hook up a fairly large number of them before you load the bus so much that it doesn't work. And this shows 6 sensors, and these sensors were spread out on my desk. When I tied them all together with a rubber band, they were all within 1/10 of a degree to each other. It's amazing how much temperature difference you can get by 4 or 5 inches sitting on your desk. This shows a little stepper motor, and it was kind of fun and easy to get programmed up and running. And they have a lot of torque, and they're only a few dollars each. So it just gives you an example. When we debug things, this was debugging the I2C interface, and I found this little oscilloscope at a place called Seed Studio in Hong Kong that was like $200, and it was actually useful for debugging the thing. By the way, they also do really cheap circuit boards, and that's who are doing our circuit boards for us now. So anyway, that's give you a flavor for it, and for more details, you really need to kind of start walking through the examples yourself. There are lots of examples on our website, and play with it. So, any questions?